Welcome and thanks for joining us for part 2 of our discussion with Dr. Ann Cox, the Quantum Information Science Technical Lead at the Department of Homeland Security's Science and Technology Directorate, Donald Coulter. He's Senior Science Advisor for Cybersecurity in the DHS S&T, Dr. Dustin Moody. He's the lead for the Post-Quantum Cryptography Project at the National Institute of Standards and Technology. And I'm Tom Tenman. It's good to have you back here with us. And I wanted to ask you, Dustin, about this idea of the moving nature of the target. I mean, where do you stand on some of this work in quantum cryptography? And I understand there's been a competition of long-standing that's nearly conclusive. So that's a lot of questions.
Yeah. So quantum computers, people have been working on them for a while, and we see progress being made in the headlines every year. IBM or Google or some other companies trying to build larger and larger ones, and they announce, I've got a machine with 120 qubits, or presumably as well, governments around the world are also trying to build these things, although they don't tend to talk about it as much. So we see steady progress. Quantum computers are nowhere yet large enough where they are threatening current levels of security, but we need to be well ahead of that. We need to be prepared way before that happens. And so that's what our project at NIST has been focused on, is having a solution ready to go before we have a cryptographically relevant quantum computer. And the way we did that is back in 2016, we kicked off basically a large international cryptographic competition. We informed the cryptographers around the world that we wanted new crypto systems that would protect us from these quantum attacks, and threw open the doors and said, spend a year designing your best things and then send them in. And we had a multi-year process to evaluate these, both internally at NIST as well as the top experts around the world. And just a year ago, we selected the winning algorithms that came out of this. We selected 4 algorithms that we're currently standardizing. And the final standards, the drafts just came out this week for public comment, and we hope to publish the final versions in next year. So industry and organizations will be able to use these standards to protect against the quantum threat.
Well, let me ask you a question, and I'm going to make an analogy here. There is a ban on the explosion of nuclear weapons for testing purposes. And so therefore, very elaborate algorithms have been developed over the years to model this, in a computer setting. And the same thing for the maintenance of the existing warheads. You can't kind of open them up and see what's going on, so they use a lot of models. How do you know these will work when there isn't a 1,400 qubit quantum computer to run them against?
Yeah, that's a good question. So the crypto systems that are designed to protect against it, they actually run on our current classical computing technology. And that's how they're designed to run. But they do need to protect against a quantum computer. And you're right, we don't have one around that we can test. We don't know how expensive it will be to operate, how fast it will run. So these crypto systems have to somehow try and take that into account and say, even if we have a big quantum computer, it still won't break this crypto system. So they have to try and extrapolate a lot of metrics of what a future quantum computer might be able to do, the number of gates that will be needed, the number of power that will be needed to run one, and provide parameters that will provide enough security to protect against this. But it's hard to do because we do not have a quantum computer to know specifics.
And I said 1,400. That number is in my mind as kind of the benchmark for what people think would be a fully functional quantum computer is 1,400 qubits. Am I making that up, or is that really the case?
No, well, it depends. So there's what's called physical qubits. That's kind of the low-level nature of it. Physical qubits then have to be organized into what are called logical qubits to do some of the more kind of computer science operations needed. They'll probably need 3,000 to 5,000 logical qubits, which correlates to hundreds of thousands of physical qubits. Right now, what we're seeing published by companies is 100, 200 physical qubits. So we're still a long ways off, but they're making steady progress.
Interesting. So it's almost the reverse of classical computing, where you could have a virtual machine and swap things in and out to make small resources bigger. You need a lot of resources to make something in a smaller quantity.
Yeah, these physical qubits have a lot of error associated with them, and they have to do error correction so that when they put them into logical qubits, the computations run and they get the answers that they know without having any error in it.
Interesting. And I just another side question. what are these computers, what do we expect them to look like? I mean, will it be a blue or gray or purple or sandstone colored box like modern current computers?
Yeah, it's pretty amazing. If you look at like what IBM have or what Google have, you can find images online of what they have. There are massive wires. They need to run in temperatures close to absolute zero sometimes in near vacuums. There's a variety of different ways people are trying to build these, and it's pretty fascinating. It's the intersection of a lot of different scientists coming together to build these things.
One interesting effort that's ongoing is DARPA has a project. They have 3 different performers with 3 different kinds of qubits to develop a usable quantum computer by the end of the decade. Now, it's not clear to me exactly what usable means, but they're using optical qubits. Microsoft has a different kind, and then neutral atom is the third one for those particular one. But there are people inventing qubits all the time, and so I think of it sort of like VHS versus beta, right? We had 2 competing technologies that essentially did the same thing. Turned out beta was better technically, but VHS had better advertising. And we kind of don't know where it's going to go. I mean, it might be that a certain type of qubit will work for a particular kind of problem. We may have like special purpose machines that are developed to solve particular problems or a particular type of problems for a while. Then maybe it'll go to a general purpose. It's really where there's a lot of the fundamental science that's been developed and the theory, and now we're kind of into the engineering phase, but of course it goes back and forth. You hit an engineering problem, you need to go then back and verify the theory. And so it's just things are moving very fast. There's a lot of international interest,
Sure.
both governmental and venture capitalists and so on.
Yeah, that degree of development, hardware, application, practicality versus theory. I had that discussion with Dr. Kuznetsov.
Yeah.
He thinks about that a lot, the director of S&T. But before I get to the question of the moving target that I want to ask you both, but you both mentioned industry here. And how much of the work is in collaboration with industry, or at least in touch with what industry is doing, because they're running after this stuff as much as the government is?
So at S&T, our philosophy for doing things is if it's available to buy, you want to buy it. If there's something that's like an 80% solution that you can adapt, then you're not going to develop from scratch. You're going to work with industry and adapt that to what you need. Only when there's nothing available are you going to go to a development project for something that's kind of unique to the government. The government market tends to not be sufficient to support a product. So what you really want is a commercial product that then you can adapt, or that the commercial part of that will do the bulk of the support for whatever item it is that you want.
Because even the basic components of what you might need for a government-specific solution, in some sense, can't outrun what is available from industry, even at the parts and pieces level.
Right.
If you needed a magnet this big that could pick up a truck, well, there is no such thing, and so you got to go somewhere else. Donald?
Yes, when we do it, what's exciting is that we do have a great innovation and partnership office that allows us and gives us kind of opportunity to share our problems with industry, ask them for input, ask them, hey, what do you have that can do this? Do you already have something? Is this related to some technology that you can repurpose or dual use for another purpose? And we definitely do identify opportunities for us to build capabilities that they didn't see a commercial market beforehand, but now you're opening up. We have government problems, and you can expand your product to address some government problems. Then you have a larger customer base as well, and then we have a kind of a proven technological basis to start from as we're building in specific, unique capabilities.
And so let's talk about that moving target aspect for science and technology. A lot of it's focused in certain domains, as we mentioned, in the ocean going, and also travel and transportation, a huge area for obviously for Homeland Security, the one most people encounter. And so that, I remember the first magnetometer. So I remember getting on a plane and you just walked on. And there was no such thing as a magnetometer, that era. But what the screening technology needed now is just light years from that early deployment of, is there metal on the person? So tell us about the changing nature of it and how your research tries to track that.
When we first started airport screening, maybe you're only looking at a magnetic signature, all right? But there's other things you need to look at. You need to look at chemical signatures. So now we have random screening that will do a swab on your hands or in your baggage and then put it in a machine. There could be electrical signatures that we want to look at. All of that is under consideration and hopefully in development, but these things take a lot of time. It takes not only fundamental research, but also there's the development piece. It costs just about as much to do the fundamental research as it does to do the development after the fundamental research is done. It's so difficult, it's actually called the Valley of Death because so many projects never make it that they've got your theory is proven and it can be done. You've got a lab version, but getting that to a commercial product is it's not trivial at all. It's a difficult process.
Right, and your commercial requirements are industrial level, high volume also, not just one of that can sit in a museum somewhere and be looked at.
So.
Yeah, that's a good point. And really that same concept expands to a lot of the stuff we do, right? We had a traditional history of thinking of traditional information technology systems. You look at the expansion of operational technologies and integration of cyber physical systems into our missions. And we have to take a broader look at what are the risks and vulnerabilities inherent to these systems that could affect them in their operations. And then what are the opportunities and decision space that we have to implement protection. So sometimes we might identify a real world physical risk to a system, but we can take a cyber action to prevent and mitigate that risk. And vice versa, it may be a cyber action or risk that we can take that we see, but we can actually just make some physical changes to the system that help mitigate those risks. So the purview and perspective of what we have to protect and the approaches that we use to protect those things are continue to evolve.
We have actually an office called SVIP, Silicon Valley Innovation Program. And they're based in Silicon Valley in the San Francisco Bay Area, but they actually work with startups around the country, and various components of DHS will present a problem to them. You never want to tell somebody how to solve the problem. You want to tell them what the end result is. Because if you tell them how to solve the problem, then you may stifle their creativity in creating a solution. And so they've been very successful in working with components and working with startups. They have a streamlined process for people to go through to present their ideas. And the government contracting process can be very difficult and take a long time on both ends, not only on the contractor end, but also on the government end. And sometimes it's like, well, we're supposed to get a budget, with every fiscal year. Sometimes that's delayed for various reasons. And that can also kind of make the contracting more difficult if you don't know when your money's coming. But they have this SVIP program that actually has been very successful in developing some things, and it's focused on startups to bring new industry partners to be able to work with them with the government.
All right, and I have some more alphabet soup at science and technology I want to ask you about, but first I want to turn once again to Dustin. You have said that quantum, aside from the cybersecurity question, is one of the great game-changing or earth world-changing technologies. How so and why so?
It'll be as disruptive as cell phones or the internet, in my personal opinion.
Yeah, just the nature of quantum physics, that it can do certain things. It can put particles in superposition and you can entangle them. And you can put qubits in superposition, so it's almost naively, you can think about it as a large number of computers operating in parallel on just a single machine with a small number of qubits. So once they're able to build this and can exploit that, it's going to give us an explosion in computational power. Now, it's not going to solve every problem. There are certain problems that it can do very well. There's known algorithms that can run on a quantum computer, but there's other problems nobody knows how to use a quantum computer yet. But there's enough of these algorithms that scientists have come up with that we already know that just this huge computational breakthrough will provide all sorts of amazing applications. And so it's in cryptography, we stay awake because it's going to break some of our crypto systems, but at the same time, we want this to come along so it'll be so beneficial to society.
Sure. And I mean, do you anticipate it, both of you, going down the path that microelectronics under the Moore's law has taken to create things no one could envision? It's created a vocabulary that, in 50 years ago, no one would have understood a word you're saying about what we talk about daily products now.
I think that we just don't know what the capabilities are going to be and what the uses are going to be. Even things like, let's say, the telephone, right? When the telephone was invented, did people envision all the uses we have for it now? I don't think so. Right?
So we'll get robo-quantum calls someday.
Oh, I hope not.
All right. Well, okay. I promised Donald a question on some of the alphabet soup here in the time we have left. CAPM, CISA Advanced Analytics Platform for Machine Learning. That's CISA. But that relates to what you're doing also.
Oh, absolutely. Yeah, we're supporting CISA in the development of research of that capability, which we do for a lot of our efforts and a lot of the CISA research and development, farther ambitious goals. We help them kind of develop and experiment and test with these capabilities. So for the CAPM program specifically, we were building up a cloud environment where we can run cyber analytics on large corpuses of data and use those to train and feed and leverage AI models to help us identify vulnerabilities and anomalous behaviors and instances on networks and systems faster than we could ever do before. So we've actually delivered the first instantiation of that that is operational within CISA that uses a single cloud environment. We're actually now working on a multi-cloud capability that leverages different commercial service provider capabilities, but integrates that into a single interface from a cyber analyst and defender perspective that allows us to use more of the unique capabilities of individual cloud service providers and also allows a broader set of researchers and analysts to access the global capabilities that provides. So that's one of the programs we're very excited about. We also have other programs that are looking at using those capabilities for our cyber analytics platform capabilities. For instance, we're using that to enhance our ability to do malware analysis and threat hunting and finding indicators. And again, the whole point of that is to enable cyber analysts to find any malware that has been delivered and find either hidden risks or even explicit risks in the software that's flowing on our networks and be able to identify that, reverse engineer, and understand what's really in a software package so we can understand what it does and how it operates and make decisions about when and where we should deploy or cut things off.
Yeah, on that cloud initiative that you mentioned, the first one, that sounds almost like the type of thing people would have tried to budget a supercomputer for at some time.
Right, yeah, so and that's the capability. And again, when you think about the evolution of computing and how we have democratized the ability to have more and more power at any individual user's fingertips because we can access a larger variety of systems, that capability only gets even that much more interesting when you think about when we get quantum computers online and the capabilities that they'll have to analyze even larger sets of information, because we don't know when those are coming along, but we do know that, as you mentioned, Moore's law, we're still, until that time, we're still going to proliferate more and more devices. Everyone's getting more connected, and there's probably tens or hundreds of devices per human now at this point. It's only going to grow a larger challenge. So having quantum computers that can kind of analyze that scale, the faster it's going to be helpful for us.
I wonder if we'll have enough electricity for qubit clouds.
Yeah, I mean, it's, sometimes in cryptography, we look at how much resources it would take to break some of these algorithms, and it starts getting into astronomical numbers where you start saying, yeah, we need more power than is on the Earth. So it's kind of mind-boggling to think about some of these things.
Yeah, I mean, look how much power Bitcoin mining takes. You know, that's probably most of the electricity, the single largest consumer of electricity that there is now.
So because quantum computers are more efficient in their computation, it may actually take less electricity when we get the advanced quantum computers than what we're using now. So it may actually help with that problem.
All right, a final question. You each get about 25 seconds to answer. We'll just go right down the line. Donald, what do you tell people at a cookout when they ask you what you do?
All right, what do? I research how do we protect all the cool stuff that you have. Bottom line. Yep.
All right, I would take that answer. Anne?
Well, I give them my job title, which is long and hard to say. And then what I really do is try to keep up with the new technology so that I understand what the threat is and so that I can make recommendations as to when to utilize the new things that are in development. And you have to look at both sides. It's not just the threat, it's also the promise, and there's a lot there.
All right, and then they ask if you want a hot dog or a hamburger or a chicken wing. And Dustin?
What do? I like to have fun with math, and the way we're doing that is we're trying to protect your communications, your data, so that even with these new quantum computers coming along, that'll all be safe. And people are always usually interested to, what's a quantum computer? So it's kind of fun to talk about.
All right, fantastic. Well, thank you all very much. I want to thank our guests. Dr. Ann Cox is the Quantum Information Science Technical Lead at the Department of Homeland Security's Science and Technology Directorate. Donald Coulter, he's Senior Science Advisor for Cybersecurity in the DHS S&T. Dr. Dustin Moody, he's the lead for the Post-Quantum Cryptography Project at the National Institute of Standards and Technology. And I'm Tom Temin. You're listening to Federal News Network. Let's go back to the studio now for more on the Cyber Leaders Exchange.